Hi friends, today we are going to learn adapter input and battery charging section in the laptops. So in the screen we can see there are few components. These are the adapter input where we connect the adapter. This is the battery, okay, and these are these are all the MOSFET number 1, 2, then 3, 4 and 5 MOSFETs are connected, and this is a chip which control all this MOSFET. Okay, so this chips normally ISL or Maxim for the battery charging and adapter input sections, for adapter input sections, and this chip is called the super input output controller. It's the manager of the entire laptop. It's a manage the temperature, voltages and all. Okay, and this chip is called the PCH platform controller hub. So we'll see how this communication take place between the chips. So first, when we connect the adapter, suppose the adapter voltage is 18, it goes into the laptop and stop here, because this is a MOSFET, this is a MOSFET source, then drain, and this one is a gate. MOSFET 1, 2, 3 is a source, 4 number is a gate, and rest pins are the drain. Okay, so when I connect the adapter voltage, the voltage stop here, then this chips voltage and power chips is require supply to work. So he'll get this voltage from this section. You can see in this animations the DC power for the chips to work this chips, and then here is a small one resistor is here, so to drop the voltages. So is a 18 volt drop here and comes out 3 volt, and this 3 volt goes to this voltage power chips as a signal, and that signal known as AC in. AC in means adapter current in, or the alternate name of the signal is called the AC detect, that is adapter current is detect. So this voltage, this signal goes to the chips. Now the chips got the power from this DC in pin, got a 18 volt, then he got the signal, that is AC detect or AC in. Once he received the signal AC in, then this chips release one signal that is called the AC OK, that means adapter current OK, and this chips send this signal AC OK signal, and this signal trigger this two MOSFET, this MOSFET drain source drain. These two MOSFETs are here. It trigger this both the MOSFET. After triggering this both the MOSFET, the voltage which is halt here, which pass to drain to source and source to drain, and goes inside the laptop like this, which you have seen in this animation. It voltage passes from this path and go inside the laptop. Okay, now there is one small resistor over here, that this resistor's value is 0.02 ohm. This resistor is called the current sensing resistor, which sense the current how much the current flowing from this section, and that current he informed to this chips. This pin is called the CSSP and CSSN, positive and negative current. He check the current and inform to this chips. So once he receive this current at this terminal, this chip is come to know that adapter current already pass to this motherboard, and then this voltage power chip communicate with the super IO and inform to the super IO that the adapter current is present, and he release one signal that is called the AC present, that means the adapter current is present. Okay, so and the second thing is in this diagram you can see there is a SM bus. SM bus is a system management bus, which is a two-wire communication protocol between the chips to chips. Is a two-wire bidirectional communications. So in this protocol, the both the chips, like here is a SIO and this voltage power chips, they communicate serially with each other. Okay, so once he receive this AC voltage, this voltage power chips communicate with this SIO and tell this SIO in other way this AC okay, that means the adapter current is present, and here you'll release a 3 volt to the SIO. Once the SIO receives this 3 volt from this voltage power chips, is come to know that the system is working on the AC adapter. Accordingly, then he is informed to his boss and he release one signal, that is a AC in signal to the PCH. Now this communications take place. In another way, SIO also communicate with this battery also. The battery have the 5 terminals, positive terminals, negative terminals, then one is a temperature, and the another two wires, that is called the SM bus. SM bus is a system management bus. It's already I told you, this is a communication protocols between the chips to chips. So here also SIO and the battery communicate with each other with the SM bus communication protocol. Okay, so here this SIO communicate with the battery and ask the battery whether he need a charge, and if the battery says yes, I need a charge, then what the SIO do, he ask to this voltage power chips to start this pulse width modulator. Here is a pulse width modulator because the battery need a charge. Now why this pulse width modulator is required here, that I tell you. See, my adapter voltage is 18 volt and my battery voltage is 10.8 volt. So if I give the 10.8 volt directly at this battery terminals, there is a chances to blow this battery, because battery is required 10.8 volt, I am giving 18 volt, so I am giving the higher volt. So I have to reduce this 18 volt, I have to reduce 18 volt, so I have to make it at 10.8. so that's why here they are using a pulse width modulator circuit. What this pulse width modulator do, this pulse width modulator reduce 18 volt to 10.8 volts. Okay, so the 18 volt coming from this path and going outside, that 18 volt coming at this terminal, so this is called a drain. And when SIO send one signal to this voltage power chip, at that time this pulse width modulator started triggering this MOSFET number 3 and MOSFET number 4. You can see in the line like this, there is a pulses going toward the MOSFET, and the MOSFET started switching, is switching this 18 volt, and this pulsating AC voltage come across this coil. Now this coil reject the DC voltage and pass the DC DC voltage, and this pulsating DC voltage come across this capacitor filter that voltage and goes inside the battery. So now the battery started charging. Okay, so battery now started charging, and battery sends signal, like suppose battery charging 50%, so he send 50%, 51%, 50, like that. As soon as the battery reaches 200, so battery sends signal ki I already fully charged, now you stop this pulse width modulator. Then this SIO sees this signal to the voltage chips, and this pulse width modulator stop like this. So in this way you can see how these sections work. Okay, so now in the second thing, now we'll see what will happen if my adapter voltage is absent. Okay, so in this case we'll see, suppose my adapter voltage is 0. Okay, adapter voltage is 0, then this AC in voltage is 0, then this voltage power chips receive the power from the battery like this in this section, and he drive this MOSFET number 5. What he do, he send one signal toward this MOSFET number 5, and when he trigger this MOSFET number, battery voltage comes out pass this MOSFET number 5 and goes inside the laptop, and in this way my voltage section power works. Thank you very much.
Hi friends, in laptops there are number of voltages are required to work all the chips. In laptop these are the voltages are required on the motherboard, like 3.3, then 5 volt, then 1.5, 1.8, 0.75, 1.05, 0.9, supposed to be CPU core and graphics core. These are the output voltages for the different chips. But in laptop there are two major input voltages, that is called adapter voltage inputs and battery voltage inputs. The adapter voltage input is supposed to be but supposed to be 18 volt or 18.5 volt, and battery voltage is supposed to be 10.8 volt. So these are the two voltages, one A for the adapter and B for the battery. So these are the two inputs, and these are the output required. To generate this output, there is one circuitry, it's called the pulse width modulator. Today we learn how the pulse width modulator works. Before to understand the pulse width modulator, first we'll understand the concept of MOSFET. The MOSFET is work as electronic switch, the metal oxide field effect transistor. There are two types of MOSFET. One is called the N channel MOSFET and another is called the P channel MOSFET. The symbol is like this. The MOSFET have three legs: drain, gate and source. The gate is a controller, and source and the drain, these are the two legs. When I trigger the gate, the source and drain get connected. I'll show you in this animations. See, in this bulb, in this circuit, you can see here is a one switch, and here I connect a bulb. When I power apply to the switch, now my switch is off, so this bulb is not going to glow. When I turn on the switch, at that time my power will flow like this, and the bulb will turn on and circuit will complete like this. So in this below circuit, here I connect one MOSFET instead of this switch. I connect one MOSFET. This MOSFET, this pin number 1, 2, 3 is a source, pin number 4 is a gate, and 5, 6, 7 it is a drain. And my 18 volt applied to the source, and when I give the gate current, that means I turn on the switch, at that time my voltage travel from source to drain, circuit complete, and turn on the bulb like that. So you can see here the MOSFET work as a switch. Now we'll understand the concept of pulse width modulator in this circuit. Here in this circuit there are two switches, switch 1 and switch 2. Then this is the coil, then the capacitor. These are the input and this is the output. Suppose if I apply 12 volt here, 12 volt DC, suppose if I apply 12 volt here, my 12 volt will go like this, it will stop here because my switch is off. If I turn on the switch, then my 12 volt straight away pass through this coil and come across this capacitor like that. Now what I am doing is, now I am switching this switch, turning on and off 10,000 times per second, like a 10 kilohertz. I am switching this switch 10,000 kilohertz on and off with a 50% duty cycle, that is turning on and off like this. At that time this DC voltage will pass through this coil and gather across the capacitor, and the capacitor store that pulse. But when this current is passing through this coil, that time the magnetic field generated across this capacitor, this coil, and my DC volt pass through this capacitor. Now there is cutting DC voltage coming from this circuit. See, the current will flow like this, so that cutting pulses gathered across the capacitor, and the capacitor connect all the pulses, and the output DC voltage will be current. Suppose I am switching at 50% duty cycle, that means my output voltage will be the 6 volt here. So it is like that. So now when my current passing through this coil, the magnetic field will be generated across the coil, and that create a back EMF, and that back EMF is on opposite direction. It's called a 180-degree shift, that current coming on the back side. Suppose I don't bypass this back current, then it will harmful to this incoming current, because my I am giving a input supply, my input current coming from this direction and my back current is coming from this direction, so it may be clash on each other. So I have to this bypass this back current. So what I have to do, I connect another switch, that is called S2. There are two switch working alternatively. When S1 is off, that time the S2 is on, and when S2 is off, that time S1 is on condition, like that. It's vice versa. When the current pass through the S1 coil, it's gathered across the capacitor, magnetic field will be generated across the coil, and the back EMF will be generated. At that time S2 will be off and S2 will be on. S1 is off and S2 is on, and that back EMF come back and goes to the ground, and in this way this switching pulses goes continuously, and this concept is called the pulse width modulator, and my output voltage will be generated. Now my output voltage depend on the duty cycle of that S1 switch. Suppose S1 switch, this S1 switch I am switching with a 50% duty cycle. That means 50% on and 50% off, 50% on and 50% off, 50% on and 50% off. At that time, if I switching like this, then my output voltage could be the 6 volt DC. If I make a duty cycle like a 25% on and 75% off, 25% on and 75% off, 25% on and 75% off, then my output voltage will be 3 volt DC. And if I switch 10% on and 90% off, 10% on and 90% off, then my output voltage could be 1.2 volt DC. So in this way we can see I get a desired output voltage in depend on the switching of my S1 and S2 switch. So I have to change my duty cycle, I'll get a difference in the output voltages, and this concept is called the pulse width modulator. Here instead of switch I am using a MOSFET. The MOSFET have a 3 leg. We already discussed the MOSFET work as a switch. MOSFET have a 3 leg: drain, gate and source. There are 2 types of MOSFETs. In desktop motherboard you can see this types of MOSFET. This part is called the gate, this pin is called the gate, this pin is called the source, and this pin is called the drain. And here there's a 8 leg MOSFET. Here is a dot, so pin number 1, 2, 3 is a source, pin number 4 is a gate, and 5, 6, 7, 8 is a drain. So here I make a circuit for switching to get my desired output voltage. Here I connect the 2 MOSFET. My voltage is coming from this side. Here I use a chip instead of using a switch. Here I am using a pulse width modulator switch, which giving the pulses to this 2 MOSFET. This is called the upper MOSFET, this one is called the lower MOSFET, coil, inductance, and then capacitor. These are the total 5 components in this pulse width modulator circuit. Here I apply a 12 volt DC from this side. That 12 volt DC come across the drain. Okay, and here's another, this 2 MOSFET connected in the cascade. Drain, source, drain, source. This point is called ground. Now when I apply a DC voltage and trigger this pulse width modulator, this pulse width modulator trigger this MOSFET, DC voltage pass through this coil, and current stored in the capacitor. When the magnetic field will be generated across this coil, the back EMF come. At that time he turn on MOSFET number 2, and that it bypass this current. So in this way this pulse width modulator work.
Hi friends, today we are going to learn how the 3 volt and 5 volt generated in laptop motherboards. This section is called always voltage sections. This is power on before power on button to be pressed. Okay, so in the last screen we have seen how voltage comes in the laptops. We've seen voltage section, voltage and battery charging section, where you connect the adapters and battery. Now in this sections we are going to learn how the 3 volt and 5 volt generated in this motherboard. Okay, so this is a concept diagram of this always voltage sections. uh, Here is a chip. This chip is number TPS 51125. These chips have the 4 departments: 2 linear voltage and 2 pulse width modulator. Linear voltage means simply when we give the input, voltage comes out. That's called the linear voltage. Okay, so now when the voltage comes inside the laptop, it goes to the different pulse width modulator, and it comes here also in this section also. 18 volt comes here like this. You can see in this animations. Okay, so 18 volt comes in, it goes to this chips, TPS 51125 chips at V in pin, and this is the MOSFET, this upper MOSFET, lower MOSFET, this is a pulse width modulator, and here also one pulse width modulator. The chips is inside this chip, this 2 pulse width modulator chips inside this TPS 51125 chips, and when supply goes to this chips, TPS 51125 chips, this chips send out 2 signal, 2 voltages, that is called 3 volt and 5 volt, and this supply is known as a linear voltage, and this pins which send this voltage out, that pin is called the VRG3, like this. VRG3, it send a 3 volt out, and VRG5 it send a 5 volt out. This VRG3 volt normally goes to this SIO. SIO now power on, it receive this 3 volt. Okay, so now SIO got the 3 volt here, it's power on. Now this 5 volt also come out at VRG5. The next is, now if you want to turn on this both the pulse width modulator, we have to give them enable signal. There are 2 enable, it's called on 3 and on 5, or it's called enable, either of this. So in some of the diagram, SIO send this enable signal, and some of the diagram, this VRG3 pins, VRG3 volt only given to this 2 inputs. Okay, so now this enable signal sent by SIO, it goes to this chip. Okay, so here is a 3 volt on the both enable pin, and now this both the pulse width modulator started triggering this MOSFET, like you can see in this animation, sending the pulses to this MOSFET, this 8-legged MOSFET. Pin number 1, 2, 3 is a source, pin number 4 is a gate, 5, 6, 7 it is a drain. This MOSFET is cascade, 2 MOSFET. This is source is connected to the drain like this, upper MOSFET and lower MOSFET. Here also same situations, is trigger this to both the MOSFETs, and this MOSFET is connected, the source and drain is connected to one junction, and that junction again connected to the coil. This is a coil, is an inductor, and what this coil do, he send out this cutting, this 18 voltage is chopping here, cutting by this MOSFET, and this chopping 18 voltage comes here and goes to this coil, pass to this coil, and when this 18 volt pass to this coil, is gather across this capacitor gather all these cutting pulses, and when current is passing through this coil will generate a back EMF, and that back EMF reverse come back again to this junction. At that time this low MOSFET turn on, and that he will bypass this voltage, particular voltage, and this DC voltage gathered here. Similarly on the same side, on the right hand side, same situation will be happen, but here the output voltage will be different. Here will be 5 volt, here will be 3 volt. So in this way we can see how this 3 volt and 5 volt is generated. Okay, after that, after completion this entire sections, this chips omit one signal, that is called the power good signal. You can see in this, it's called a PG, or the power good. Power good section means this particular department is working fine, it's working okay. So In this way, this 3 volt and 5 volt is generated in this motherboard. So here I mention sequence, like pin sequence number 1, this chip supposed to get a 18 volt at V in pin. Sequence number 2, this chip supposed to send two output signal, that is called a VRG3 and VRG5. VRG3 is supposed to come 3 volt and VRG5 5 volt. Then next is, as I got the power, the next is enable signal on 3 or on 5, or enable signal, either of any of this name. It should get a 3 volt. Fourth, then fifth, chips sending the pulses toward the MOSFET, triggering the MOSFET gate, both the MOSFET upper low gate and lower gate, both the MOSFET, pulse setting DC voltage gathered, passed to this coil, output volt gathered across the capacitor. That is a 6 steps. At 7 steps, power good signal comes out, and that means 3 volt comes out from this PG or power good. That means the entire section is working fine. So in this way this sections work. Thank you very much.
Hi friends, today we are going to learn how to repair a dead laptop motherboard. Okay, so you can see on the screen there are 3 sections: section A, section B and section C. The section A is called the built-in battery charging sections, where the 2 input supplies are connected. One is an adapter and another is a battery, and this voltage goes inside the laptop. Okay, these are the output junctions where the voltage goes inside the laptop. It goes to the different sections. This voltage is controlled by this 2 MOSFET, this 2 MOSFETs and this MOSFET number 5, and this is the controller chips who can manage this. All these are the MOSFETs. Okay, so the section B is called the always voltage section, which generate a 3.3 and 5 volt before laptop power on. In this section there are total 4 department, 2 linear regulators and 2 pulse width modulator. We are using here TPS 5W125 chips. These are the pulse width modulators, side 1 and side B, 3 volt and 5 volt, and inside there is a pulse width modulator chips and 2 linear regulator. Okay, and section C, this section is responsible for power on the laptop. And this sections we can see there are mainly 3 component. One is called the PCH, another is the SIO, and third is the EC bias. Okay, so this 3 chips require a 3 volt to operate. They require 3 volt to turn on, so they should get 3 volt before power on the laptop. Now once I connect the adapter from this DC jack, if I power on the adapter, the voltage goes inside the laptop and the voltage cross these 2 MOSFETs, cross this current sensing resistor. Here is a current sensing resistor. The value of this current sensing resistor is 0.002 ohms, which is a very minor value to sense the current of the laptop. Okay, so when I connect the adapter, voltage goes like this. You can see in this animation, this is my first test point where I can check this 18 voltage across this current sensing resistors, and this voltage goes out. Okay, so this 18 volt goes next sections. This section is called always voltage sections. In this always voltage section there are 4 departments, 2 pulse width modulator, like this you can see on the screen. This is a pulse width modulator and this is another pulse width modulator. This voltages comes before power on button press. This section generate a 3 volt and 5 volt, and there are another 2 voltages comes out from this section, that is called the 2 linear voltages, that is called 3 voltage linear and 5 voltage linear. Okay, so that means there are 4 voltages comes out from this sections. So once the 18 volt goes inside the chip, this chip is, we are using here TPS 5W125. This 18 volt goes, the pin is called the V in pin or the B plus pin. 18 volt goes inside, and this chip send the 2 voltages out.
that is called VREG3. You can see this VREG3, that is 3 volt comes out, and VREG5. Okay, so VREG3 volt goes to this here, it's called the SIO, and EC bias. This goes to SIO and EC bias. We have to check 3 volt at here at VREG3 pin. 3 volt, if this 3 volt is coming, then this IC probably okay. If 3 volt is not coming, that means this IC may be the faulty, so you have to replace the chip. Then this 2 pulse width modulators are here, and to turn on this pulse width modulator is require enable signal. Here is everything is in digital format, like 3 means high and 0 means low. So to turn on this pulse width modulator, this chips require a 3 volt enable signal. This 3 volt enable signal is get from either a SIO, or he generated himself from, it takes from this VREG3, and it depend on the circuitry. Okay, so this 3 and 5 voltage coming across at this capacitor. This is a VREG3. This voltage is called a 3.3 always, and here is a 5 volt always. Okay, so here we can see the 3 volt coming at the SIO as well as EC bias at pin number 8. Now the next is to turn on the SIO. The SIO requires basically 3 things. First is need a power. Second, he need the EC reset. The EC reset generated by this RC circuit, it require a 3 volt here, 10 millisecond delay, 3 volt. And the third is clock, 32.7 kilohertz oscillation clock. Either he generate by himself by using a crystal, or it borrow from the PCH. The next is, this is the power button. It's called the NBS on, power on switch. Here is a 3 volt here, and the power on switch is here, and this is called the ground. Now if I connect the 3 volt to the ground, it's become a 0 volt. So when I press the power button like this, it generate a 303 pulse at the SIO pin, this NBS on pin or power on pin. When he received this pulse, SIO send one pulse. This pulse is called the PCH power enable, and he send this 3 voltage to the PCH, because PCH not got the power as yet. So now after pressing the power button, the SIOs generate one pulse, that is called the PCH power enable pulse, to this MOSFET at gate, and this 3 volt here, it goes to the PCH. See in this animation, this 3 volt going to the PCH, and this voltage we can check at this capacitor on the PCH. If this voltage is coming at the PCH 3 volt, that means PCH is getting the 3 volt. Okay, so the next is, once the PCH got the power, in a few milliseconds the PCH get another signal, that is called the resume and reset. Now it's a 0 volt, now it's become a 3 volt. It got a resume, it's called the RSM RST. And if the RSM RST is not coming, if it is stay 0 only, that means the problem probably either in SIO or the EC bias. We have to flash the EC bias and check, or we have to change the SIO. If it is coming, this RSM RST is coming, that means my both the things are working properly. The next is, once the RSM RST is received, in a few milliseconds, SIO send another signal to the PCH, that is called a PM power button or a DNB power on signal. This signal, it's 303, he sent one pulse 303. So this signal is saying to the PCH that key power button is pressed. Now we have to turn on the power. So what to do? He asked the PCH. He sent this pulse. Now the PCH respond, and PCH will send the two signal, that is called a slip mode 4 and slip mode 3. Now this both the voltages are 0, both the signals are 0 here on the SLP S4 and SLP S3 pin. You can check on this SIO. This is called the SLP-S4 and SLP-S3. If it is the PCH is okay and if PCH found is everything is okay, then he send this two signal that is called SLP-S3 and SLP-S4 signal to the SIO. Okay, it's become a 3 volt. See in this animation you can check 3 volt at SLP-S4 and SLP-S3 pin, and if it is coming, that means your PCH is responding properly, is everything is okay, everything is going nicely. And if this voltage is not coming here after power on button press and after PCH received this PM power button signal, that means my PCH may be the faulty, then we have to replace the PCH. The next is, once SIO received this SLP, S3 and SLP4 signal, he is sending 3 signal one by one, that is called a suspend on, then system on, and then VR on. These all signals are now in 000 volt. After he has received this 2 signal, he send one by one signal like this: suspend on, then system on, and then VR on. And that's particular pulse width modulator started turn on, and they are running. After that, once he received everything, once he sent everything, the SIO received one signal that is called a IMVP power grid. The IMVP power grid, that means the VRM power grid, that the core section is okay now, all the power section is okay, and finally he will send one signal, and that signal is called EC power okay to the PCH. It's called EC power okay, or call the PCH power okay to the PCH. He's sending this signal here. It should be a 3 volt. That means all the power supplies are okay. Okay, so in this way we can see how to check a dead motherboard, how to. So now we are going to check on the schematic diagram how the sequence works. Just now we check on the concept diagram how we are going to check the signals on all the voltages on the motherboards. Okay, and now we open a schematic diagram, and we'll see on the schematic diagram where we are going to check all the signals. Okay, so we are open this Completo motherboard. This motherboard name is LA7981P. Okay, and this is a 64 page diagram. In the second page, this is a block diagram. The CPU is, this one is a processor, Intel Ivy Bridge 3rd generation socket 988B, Panther Point HM75. This is a PCH, and SIO is a ENE KB9012 is a SIO. In this SIO, EC bias is inside this SIO. Okay, so we are going to check if this motherboard is dead, and what are the test point we are going to see now. Okay, this is a page number 2. In page number 49, now we'll go to the page number 49. This section is called the volt-in section. Okay, volt-in power in section. We'll zoom this section. Here is our adapter input. Okay, this is my adapter input. This is my adapter voltage, 18 volt or whatever it may be, 18.4 or whatever. So the voltage from here, this one is a MOSFET. MOSFET location is LPQ301 and PQ302. Okay, this one is a drain, this one is a source, and this one is a gate. This gate is controlled by this chip. This gate is controlled by chips. This chip's location number is, this chip is location number is PU301 and the chip number is BQ2472. Okay, so once he received, this chip is received the AC detect signal, he drive this MOSFET, this 2 MOSFET he drives, trigger this gate, and the voltage travel from this MOSFET is cross this both the MOSFET and voltage comes across this resistor. This is my first halt. Here I should get 18 volt here. Okay, this location number is PR302. Location number is PR302. Here I should get 18 volt. If it is 18 volt is not coming here, then possibility either of this one of this MOSFET may be the faulty or is not getting trigger from this chip. Okay, so here I have to check this voltages and this chip, and if the voltage is coming across this resistor, then this section is okay. Then we have to go to the next section, that is called the always section, that is on the page number 50. So we'll go to the page number 50. Now this is a page number 50, and this section will create a 3 volt and 5 volt. This sections generate of totally 4 voltage, 2 linear voltages and 2 pulse width modulator. Okay, so in this location is a PU401 and this chip number is RT8205. It's similar to the RTPS 51125 just now we have seen our concept. So this is our pin number 16 is a VIN input where 18 volt is supposed to come. This VIN pin number 16 is 18 volt supposed to come when we connect the adapter. And if the chip is okay, then he send the 2 voltages out at the VRG 3 at pin number 8. Here I should get a 3 volt, and this VRG 5 pin number 70. Here I should get a 5 volt. Okay, and this 3 volt goes to the SIO. We'll see later on. And the next is these are some pulse width modulator, 2 pulse width modulator. You can see this is a pulse width modulator here and here inside the pulse, and this pulse width modulator enable signal to power on. Here you get enable signal, and once you get the enable signal from this pin, this section will start, and here generate a 3 volt always, and here a 5 volt always will be here. Okay, so in this way 3 volt and 5 volt is generated, and if it is not coming, then we have to check this section. Okay, and if this voltage 3 volt is coming out, this 3 VLP goes to the SIO, as well as this 3 volt always also goes to the SIO. The next section will go to the SIO, the page number 42. This is page number 42. My SIO location number is U31 and the SIO number is KB9012. This is my SIO number, and this 128 pin chip. First I have to check pin number 111, that is 111 pin. Here I should get a 3 volt, that is come from always voltage 3 VLP, and the secondly I have to check pin number 9, 22, 23, either of any of this pin I should get a 3 volt here. Once this chip get this 3 volt, then it will start function, but before that he need a reset also, that is called the EC reset. Okay, so this is a EC reset. You can see on pin number 37. This one is the RC circuit. Here is a resistor, 47 kilo ohm resistor, and this one is a capacitor, 0.1 microfarad capacitor, and here is a 10 millisecond delay. We get a EC reset. Okay, then this chip will start for function. Okay, so now the next is, once he received the EC reset, next we have to press the power button. The power button on the page number 114. We can find where it is. See, in the on off here, 114. This is the on off switch. 114. This is my on off switch. Here I should get a 3 volt, and when I press the power button, it goes to 0 and come back again to the 3. That means my power switch is okay. The next is once you receive this power on button, The next is this SIO send one signal that is called the PCH power enable. Okay, the PCH power enable, that is called the PCH power, and we'll find where it is. PCH power enable. See this one, 119 PCH power enable. Once the power on button is pressed, here I should get a 3 volt. If I get a 3 volt, that means my SIO is responding. 119, pin 119, here I should get a 3 volt after power on button is pressed. That means the PCH will receive the 3 volt. The next is my PCH, this is PM power button, that is post power button. It's called the digital power button. It's called the DN power button. The next is DN power button. That is this one, pin number 106. Here I will get a 303 pulse after PCH power enable signal. The next is RSM RST, resume and reset. RSM RST, see RSM RST, pin number 100. I have to check pin number 100. After power on button press, I should get here 3 volt. If 3 volt is not coming at this pin number, that means possibility either my SIO is bad or my EC bias is corrupt. So I have to flash the SIO bias, EC bias first. If the problem is not solved, then I have to replace SIO. The next is power button. Okay, this PM power button 106. The next is when now PCH got the information that power button is pressed. Now the turn of PCH to give two signal to the SIO, that is called slip mode 3 and slip mode 4, that is called SLP-S3 and SLP-S4. Here is a SLP-S3 at pin number 6. I should get here 3 volt and pin number 6, and here is a SLP4 at, yeah, see, SLP-S4, PMSLP-S4. If I'm not getting a 3 volt here, that means possibility that my PCH may be bad. So I have to check PCH, and if it is voltage is coming, that my PCH is responding. 127 and pin number 6, SLP-S3 and SLP-S4. The next is my SIO will turn on all the voltages one by one. First he'll start system on, then suspend on, then VR on. Same signal like this, SUSP 116, then system on, pin number 95, and finally VR on 121. This signal come one by one. Okay, so after every signal as comes out, then the SIO will get the confirmation everything is okay, the VRM power good is okay. Then finally SIO send one signal that is called the PCH power OK. This signal from pin number 32, there is a final signal saying that all powers are okay, now proceed for the reset signal. So in this way we can check a dead motherboard, and if one of the signals is missing, then you have to check accordingly. Thank you very much.
Hi. Today what we'll do is, today we'll learn how this power sequence flow in any motherboards. So these are the ladders where all the signals flow. So first, when you connect the adapter to the any laptop, first the power comes, and that power is called the always voltage. It's called the always voltage. It goes to the SIO and the PCH. That voltage is supposed to be 3 volt. And before power on, you should get a 3.3 and 5 volt at the always section. Okay, so this is the first steps. So before turning on the laptop, turning on the switch, you should get a 3 volt on any laptop, and this voltage is called the always voltage. And when you turn on the switch, then the all voltage comes out, the voltage 1.5, 1.35, 1.05, 3.35, graphics and CPU core, and it goes to the particular switch to the entire motherboard. So these are the power. This voltage comes before power on, it's called the always voltage, and this voltage comes after the power on. Once the motherboard gets the power, the next signal is generated, that is a power good. The power good signal, it's called the confirmation signal that all power planes are steady now and they are ready to work, and that signal is called the power good. After that, the motherboard get reset. In motherboard is a combination of lakhs of MOSFETs. So the reset signal, what he do, he's a clear all the junk information on the motherboard. He clear the RAM, clear the CPU, clear everything on the motherboard and keep ready for work, and that signal is called the reset signal. There are 2-3 reset. One is called the PLT reset, it's called the platform reset. Another is called the CPU reset, then the PCI reset. After the reset, motherboard is ready to work and motherboard get the clock. The clock, it's called the frequency, the different frequencies the motherboard have, the CPU, then PCH, then BIOS, and then SIO, then RAM. All these different chips require different frequencies. Okay, so the clock department, what he do, he provide a different frequencies to the entire motherboard. So that job is a clock department. After that, BIOS start reading, CPU access the BIOS and read the BIOS. So BIOS do the startup work. He just do a startup, just like he do the self, and he do a post. It's called the power on self test. He tests the all devices are there or not. He tests whether they are working or not. They initialize them and they are ready to work. That is the job of post power on self test. And the last, after the post completed, if it is any error, then BIOS generate a code that is called the error code that we can see on the debug card. And if you pass that this power on self test post code, then the display will be appear, and in this way this flow is go like this in this any motherboards. Yeah, in the next is in the entire motherboard there are multiple pulse width modulator. These are the different pulse width modulator, right? So here are 2 pulse width modulator for 3.3 voltage, 5 voltage, and here is a pulse width modulator for 1.5 voltage, 1.8 volt, 1.05 volt. This is for the graphics chips, graphics core volt, and this one is called the CPU core. CPU core require a higher current, is require more than 20 ampere. So here are the 2 pulse width modulator provided to the CPU. And the next is, this is called for the battery charging purpose. So here are, you can see there are different pulse width modulator for the different sections on the motherboard. So in this next screen we can see this different pulse width modulator goes to the different power, like this is the always voltage is generated 5 volt and 3 volt. This 3 volt goes to the SIO, this always voltage, and here is a MOSFET. This side voltage is called the always voltage and this side voltage is called the suspend voltage. Why it's called the suspend voltage? Because this voltage turn on or goes out when you press the power button. Okay, so that's why it's called the suspend voltage. This suspend 3.3 goes to the BIOS, then the PCH, then the RAM, and this 1.5 voltage, this is also generate after turn on the power button. This 1.5 volt goes to the PCH, then this 1.3 volt goes to the DDR3L RAM, and the processor 1.05, that is this is system voltage, is goes to the PCH and it goes to the CPU. And finally this is called the CPU core section. There are 2 voltages, one is called a CPU core voltage and another is called the graphics core voltage. There are the 2 voltages goes to the CPU. So this different pulse width modulator generate a different voltages and it goes to the particular chips on the motherboard. So have you seen how this section is work? In next diagram we'll see how this next section work. These are the main manufacturer of the motherboard. There are 4 main manufacturer on the motherboard in the world. this is called the Completo motherboard. The Completo motherboard numbers start from LA something something something. It's called the Completo motherboard. Then this Quanta motherboard. The Quanta motherboard numbers start from this DA0 or something R. R is indicating and something something number, that is called the Quanta motherboard. The next is called the Wistron motherboard. Wistron motherboard number 5-digit number and then -1 or -2 or -3 like that. And this next is called the Inventec motherboard. So long numbers. So these are the main 4 manufacturers of the motherboard. Okay. So when we open any laptop, you can see this number located on the motherboard, any of this corner. So you have to locate the number, and from that location you get the diagrams. You can download the motherboard from any of the site or the pay site or free site, whichever is convenient to you. You can download the schematic diagram. These are the 4 main manufacturers of the motherboard. So next is now what we'll do is we'll see this Completo motherboard. This is a Completo motherboard, a flow chart, and in this motherboard we'll see the how power plane flow, how this voltage flow, how the signals are flow, and how can we repair a dead motherboard in this any Completo laptop motherboard. Okay. So first I'll introduce the component. This is the processor, CPU, then this one is a PCH, then this one is SIO, this is a BIOS, and these are the 2 inputs. One is an adapter, another is a battery. This voltage section, this adapter and battery charging section is called the voltage section, is here. Any one voltage goes inside. If we connect the both voltage, if it is adapter and battery also there, then only one voltage pass. Okay. And these are the different pulse width modulator. This always voltage is that there are 2 pulse width modulator, one for this 3 volt and another is for the 5 volt. There are 2 pulse width modulator, and this voltage is generated before power on. The next is this is for 1.5 voltage, basically for the RAM. If it is a RAM or DDR3L, then here voltage will be 1.35. If it is a RAM DDR3, then here voltage will be 1.5 volt. Then next is 1.8 volt, 1.05. This is the system voltage. And finally this is called the CPU core voltage. In CPU core there are 2 sections. One is for the graphics core and another is a CPU core. So these are the different pulse width modulator, and here are 2 MOSFET. This side voltage is called the always voltage, and this side is voltage called the suspend voltage. Now if I connect the adapter, my 18 volt goes inside and it goes to the different pulse width modulator. You can see in this animation my 18 volt pass to the different pulse width modulator. It goes to the all the input sections. Then this section won't work unless they won't get a enable signal. They won't work. This particular section will work, and he will generate this 3.3 and 5 volt. You can see in this animation this 3 volt and 5 volt is generated, and this 3 volt goes to the SIO, and this 3 volt goes to the EC bias if it is there, otherwise only SIO. And this both the voltage are stopped here by 2 MOSFETs, because this side is voltage called the always voltage. This voltage turn on before power on switch, and here is also 3 voltages stop. So now the next is called my power button. Then my third step is power button, that is called a EC power button, power on, or NBS power on, something like that. Or there are maybe 2-3 names given for the power switch. Either are NBS W on, power on, or on off switch. Okay, so here you can find 3 volt and the another leg is connected to the ground. Okay, now this is when I press the switch like this. You can see in this animation, when I press the switch, my 3 volt goes to 0, and if I release that button, my 3 volt goes to again 3. So 303 pulse will be generated at this power on button. Once SIO get this pulse, what SIO will do, he generate the next signal, that is called the PCH power enable. He generate the PCH power enable and trigger this MOSFET. he trigger this MOSFET. After triggering this MOSFET, my voltage will pass this MOSFET and goes to the PCH, and PCH got the power. And this voltage I can check. If it is HM55 PCH, then this voltage I can check on this capacitor. Okay. So after the 10 millisecond delay, my next signal will be generated, that is called the resume and reset. Here before power on switch, here I get a 0 volt. After power on switch, I should get a 3 volt. That is called the RSM RST. If my my entire section is working, then here I should get a 3 volt. And if I get a 0 volt after pressing this button, that means probably my fault could be either SIO or my EC bias, something related to this. So I should get a 3 volt here. Okay. Once SIO generate RSM RST to the PCH, PCH get reset, his power plane is ready to work, power management ready to work, and within a next microsecond SIO generate the another signal, that is called the PM power button, or it's called the DNB power button, or it's called the PM power button. This is called the post power button, or it's called the digital power button, that saying SIO to the PCH ki power on button is pressed, you ready for work, or give me the permission to turn on the laptop. He is asking to PCH. So here firstly here is a 3 volt, then it goes 0 and again back to the 3. So 303 pulse generated at this pin, that's called the PM power button. The next is when the PCH got the signal PM power button, now the PCH has to reply to the SIO. He has to give the answer to the SIO. So PCH, what if everything is okay, if everything is ready and power management is ready to work, what the PCH do? He send the two signal, and that is called slip mode 3 and slip mode 4. He send the two signal SLP S3 and SLP S4 like this. He sent the two signal. Here previously it was a 0 volt before power on, and now it's become a 3 volt here. I should get here 3 volt on. We can check all these voltages on SI only, because we can't check the PCH directly. So we can check all this voltage on SIO pin. Okay, so I should get here a 3 volt. If a 3 volt is not come here after PCH getting this signal, that means probably my fault could be PCH could be bad. So I have to check like that. So if it is a 3 volts comes here properly, that means PCH given permission to the SIO to turn on the laptop. The next signal is when SIO got this confirmation from the PCH, he generate the next signal, that is called a system power on or sys on. The sys on signal generate and give the enable signal to this pulse width modulator, and then this 1.5 volt will be generated, and this 1.5 volt goes to the RAM, PCH and the CPU, all three chips. This 1.5 goes to the CPU, PCH as well as RAM. The next signal is within a few microseconds, SIO generate the next signal, that is called a SUSP, that is called the suspend on. He generate the next signal on the 10th section. He generate the next signal, that is called the SUSP. When the SUSP signal is generated, he trigger these 4 sections. Firstly, he trigger this MOSFET. He trigger this MOSFET gate and pass this voltage to this side, that side, another side, and this 3 volt become a 3 volt suspend, and it goes to the entire motherboard. This 5 volt become the 5 volt suspend, and it goes to the entire motherboard, like a hard disk, DVD writer, fan, everywhere it goes to the outside. Okay, the next is he trigger this 2 section, that is called a 1.8 volt. He turn on this 1.8 volt, that is called a system voltage, and then the next is called the 1.05 voltage. This is also system voltage, and this 1.05 voltage goes to the processor as well as to the PCH, and now the PCH ready to work. Once he generate the 1.05 volt, this 1.05 volt pulse width modulator generate a power good signal, and this power good signal goes to the SIO, and this signal known as SA power good. SA power good, and this SA power good means all the power streams are okay. SIO will not turn on the power unless he get this signal. SIO turn on this signal, he turn on the VR on signal, sending this VR on signal on 11 step, but he wait till this signal he should get. Okay, he should get this SIO power good signal. Once he get the SIO power good signal 3 volt at this pin, SIO will generate a VR on signal at 11 numbers. He turn on the CPU core section, turn on the CPU VR on section, and CPU core generate a graphics core. It's sent to the CPU, and finally send the CPU core voltage. That is supposed to be approximately 0.8 or 0.9 volt. It goes to the CPU. It's with multiple ampere, something 20 to 30 ampere to the CPU core and 20 ampere to the graphics core. After getting this CPU core and graphics core voltage, CPU communicate with this VRM section, and this protocol is called the SVID. SVID means serial voltage identification signal. Serial voltage identification signal. He communicate whether the power which is sent by the CPU whether it is correct or not. If it is not correct, he inform to the VRM section, okay, I need this much of power. So he communicate with the VRM section, and once this voltage gets stabilized, CPU got proper power, this VRM section generate a signal that is called the V gate, or it's called the VRM power good. The VRM power good signal means this VRM section is working fine and CPU got the power. He generate this VRM power good signal at step number 13. Okay, and in step number 14, SIO generate a signal that is called the PCH power okay, saying PCH to that I done my job and all power planes are working fine. So he generate this PCH power okay signal, and here the both signal will connect each other, and the one final signal is generate that is called a system power okay at step number 15. The system power okay signal means the all power sections are okay. If you check this voltage here 3 volt, that means you no need to check all these voltages. If this voltage, if this signal is coming, that means the entire power planes are perfect, working all right. If this voltage is not coming, then system will be halt, it will go ahead. Okay, once PCH got the signal, then PCH started generate this 3 signal one by one. So he first sent the DRAM power okay, saying CPU that RAM got the power and RAM is connected to you and you start communicate. So he send a RAM power okay, and then he will send a CPU power okay, and he will tell the CPU that whatever all the 3 power, CPU got the 3 power, that is called the VCCP, then VTT and CPU core. He says the CPU that you all powers are okay and you ready to work. And finally PCH generate a next signal that is called the PLT reset or the platform reset, and in platform reset he reset the entire motherboard and he reset the CPU also. He reset the CPU also, and once the CPU gets reset, CPU ready for work, and he access this DMI bus and like this and access the BIOS. So in this way we seen how this laptop's power sequence work. Suppose if your laptop is dead, if it is not working, it's not power on, so what you have to do, you have to check this 3 volt first on the DC power supply, or you connect to the DC power supply, check the current, and if you don't have a DC power supply, connect the adapter, open the laptop and check the voltage at SIO pin number VCC pin, or you can check on the EC bias pin number 8 also. 3 volts supposed to come. If 3 volt is coming on the SIO, that means your always voltage is working fine. The next step what you have to do, you have to check power button voltage, and your power button you should get a 3 volt,
Once you press this 3 button, it goes to 0 and come back to 3. So there will be pulse will be generated at power button. After power button press, you should get the RSM RST signal. If this signal is not coming, then problem possibility either your SIO or US bias may be corrupt. So you have to reprogram the EC bias or change the SIO. And if this signal is coming, then you can straight away check this SLP3, SLP4 at pin SIO pins, and here you should get a 3 volt on the both the leg, SLP S3 and SLP S4. If it is these signals are not coming, that means the possible fault could be the PCH. Okay, the possible fault could be the PCH. If this signals come, then SIO turn on one by one signal, that is, you turn on the SWIS signal first, SUSP signal second, and lastly turn on the VR on signal. But before turn on in the VR on signal, you check this signal whether he got the signal or not. And then finally he will generate the system power OK signal, then power is all the plane, and he generate this 3 signal. So in this way, this Completo motherboard power sequence work for almost all this generations. Thank you very much. Hi friends, today we are going to learn Quanta motherboard power sequence. In this screen you can see there are components like this one is called the CPU processor, then this is a PCH, and the next one is SIO. Now today we learn Quanta motherboard power sequence. First we'll see how to identify the Quanta motherboard. Okay, so see in this screen you can see there are 4 types of motherboard. There's a Compil, Quanta, Inventec and Westron. So the Quanta motherboard number start from like a DA0, R13 or R33, R53 like that, and Compil motherboard number start from LA, and Westron motherboard number start from like a 5 digit and -1 or -2 or -3 like that. So any laptops require all these types of power. Suppose CPU require a 4 level of power, CPU require a 1.35 voltage if the DDR3L RAM, then 1.05 volt, then graphics core and CPU core. Then if the RAM is DDR3L, then RAM require a 1.35 volt, 3.3 volt, 0.75 volt. PCH require a 1.05 volt, 1.5 volt, 1.35 volt and 3.3 volt. Biases require a 3.3 and SIs require a 3.3, and these are the different pulse width modulator. In there are I already told you there are different manufacturers of the motherboard like Compil, Quanta, Westron, Inventec, and they have a different power sequence. Okay, these are the basic concept of the pulse width modulator, and they follow the different sequence to flow the power. So here in the screen you can see the power sequence of the Quanta motherboard. I mentioned here from number 1, 2, 3, so it's very easy to understand. And these are my different pulse width modulator. Like this here is called always voltage, which generate a 3.3 and 5 volt. Always voltage means this voltage generate before power on. Means if you give a power, like if there is an adapter or whether it is a battery, this supply will be generated. So that is why it's called always voltage. This voltage is called the suspend voltage. This voltage is called the suspend voltage because this voltage is already generated, but when you press the power button, this voltage flow on the motherboard. And this rest of the voltage are the system voltage from here to here, like a 1.5 volt, 1.05 volt, 1.8 volt. The 1.5 volt goes to the CPU, RAM and PCH. If it is a DDR3 RAM, then 1.5. And the next voltage is called a system voltage, that is a 1.05 volt, and 1.8 volt that is goes to the CPU as well as to the PCH. This voltage is called the CPU core voltage, which generate something around 30 to 40 ampere current for the CPU core. The voltage level is something 0.9 volt, and the next voltage, that is a graphics core voltage, that is also same, something 9 volt. So these are the different pulse width modulators controlled by this chip. That is, this chip is called the Super IO, SIO. It's called the EC embedded controller also, or it's called the KBC, keyboard controller. Now we'll see how this power sequence take place. So these are my two inputs. One is adapter, the second one is the battery, and this is my the voltage section where laptop receive this 2 power. When the laptop receive this 2 power, he send out 1 power out. This voltage is called the voltage section, V in voltage, or it's called the B++ voltage. That's supposed to, if the adapter and battery both are connected, then I will get here adapter voltage only, and if the adapter is voltage absent, I will get here a battery voltage. That is, a battery voltage supposed to be 10.8 volt or 11.1 volt, like that. So this 18 voltage goes to the different pulse width modulator. It goes to the always voltage, goes to the 1.5, it goes to the 1.05, 1.8 and CPU core, all the input section. In the pulse width modulator, I already explained you in the other video that how the pulse width modulator work. You can see that video also to understand the pulse width modulator. Now when the 18 volt is received to the different section, this pulse width modulator, only this section will respond. That is called the always voltage will respond, and he will generate a 3 volt, that is called the linear voltage. 3 volt linear voltage will come out, and this 3 linear voltage goes to the SIO. SIO is the entire manager of the laptop. So he receive the power, it's called the always voltage, or it's called a VCC voltage. In desktop motherboard, it's called a VSB voltage, 3 VSB. Okay, so SIO receive this power, 3 volt is received, and then the SIO wait to press the power on button. My next step is the power button. The power button, I'll get a 3 volt, and this the switch, one end is a 3 volt, another end is connected to the ground. So as soon as I press power button and I release that power button, here is a 303 volt pulse is generated, and it goes to the SIO. This pin is called the power button, NBS on and power on, like that. So you can see in the schematic also. I'll show you in the schematic also. So 303 pulse will be generated at this point. Once he receives this pulse, SIO omit one signal, that is called SLP S5 signal at the step number 4. He omit one signal, he send out a 3 volt. This signal is called the slip mode S5, and he turn on always voltage. In always voltage, there are 4 section, 2 linear regulator and 2 pulse width modulator. One linear regulator, that is a 3 volt, that is called the VL voltage. This voltage goes to the SIO, and this 5 volt comes out, that is called a 5 volt VCC, that goes to the subordinate component of the always voltage. Once SIO send out this SLP S5 signal to the always section, he start up 2 pulse width modulator, and this 2 pulse width modulator started, and they generate a 5 volt and 3.3 volt, and this voltage will be halt here, and this 3 volt goes to the PCH also. That is my step number 4. Once always voltage generate this 3.3 and 5 voltage, this 3.3 and 5 voltage will be generated, and this 3.3 voltage goes to the PCH, and this voltage will halt here. The next thing is, once the PCH got the power, SIO generate a next signal, that is called the RSM reset. It's called the resume and reset. See, there are few reset signal. First of all, it's called the EC reset. The EC reset require to the SIO to work, that is generated once SIO receive the power. The next is PCH require a reset signal. That reset signal is called the resume and reset. So in Quanta motherboard, if your motherboard is not powering on, suppose if you press a power button and your laptop is not powering on, then you can straight away check this RSM RST signal. The RSM RST signal should be 3 volt. It should come out the 3 volt, and if this 3 volt is not coming out, that means your problem, probably your SIO, or problem your maybe the EC bias, or SIO not getting the power, or SIO not generate the EC reset. These are the few problems you can see. So once you press the power button, the next signal you have to check the RSM RST. Once the RSM RST comes within a few microseconds, SIO generate the next signal, that is called the post power button, that is called the PM power button, or it's called the DNB power button. That 303 volt pulse generated at this point, and this 303 pulse goes to the PCH. So once the PCH receive this signal, and he will understand ki SIO now asking to turn on the laptop. So once he receive this pulse, now the PCH will give the confirmation signal to the SIO. That signal is known as SLP S3 and SLP S4. These two signals sent by the PCH to the SIO. These are the two slip mode, SLP S3 and SLP S4. SLP S4 is basically purpose for the turn on the system voltage, and SLP S3 is used basically turn on the VRM voltage. Okay, so the next thing is they have an alternate name also. In some time you don't find this SLP S3 and SLP S4 signal, but in that case you will find the another name. It's called the SUSB and SUSC. These are the alternate name for the SLP S3 and SLP S4. So once SIO received this two signal, or it's come from 0 to 3 volt from PCH, now SIO now turn to the SIO. Now he will turn on the supply one by one. So it's first turn on sys on signal. He trigger this two MOSFET. My 3 volt and 5 volt is generated at this junction. This MOSFET has not passed to the entire motherboard. But once SIO omit this signal, as sys on signal he generate at 9 step, this 3.3 volt pass to from drain to source, and this 5 volt pass from this drain to source. So this voltage is called the suspend voltage, and this voltage spread entire motherboard. So the next signal is called SIO omit another signal, that is called sys on signal. Once SIO omit this sys on signal from 0 to 3 volt, my 1.5 volt will be turned on. My 1.5 pulse width modulator will turn on, and he will generate a 1.5 voltage, and this 1.5 volt goes to the RAM, PCH and CPU. So the next is SIO omit the 11 step signal, that is called a main on signal, and that main on signal he trigger this two pulse width modulator, that is called a 1.05 volt and 1.8 volt. He turn on this enable, gives the enable signal to this two pulse width modulator, and this pulse width modulator generate the signal that is called a 1.05 volt and 1.8 volt at step number 12. Now you can see in this different pulse width modulator generating a different voltages, and their power good signal reach to this point. All the pulse width modulator generate a power, and their power good signal collected at this point. It comes at this point. So once suspend on signal will generate, it send the power good signal. Always voltage power good signal goes there. 1.5 volt power good signal goes there. System voltage power goes there. It like that. So once all the powers are fine, all the powers are working okay, and that point here 3 volt will be generated, and this 3 volt signal is called HWPG at step number 13. If one of the voltage is absent from this line, your voltage will be 0 volt, and if the all voltage coming proper at this point, here will be 3 volt will be
generated, and this signal is called HWPG. That's step number 13. After that, once SIO received this HWPG, he turn on a VR on signal. Otherwise, he won't turn on the VR on signal. The VR on signal will be start lastly once all this power comes out. So before turning on the CPU core voltage, SIO check all voltage should be on proper line. The next is he turn on the core voltage, and this two CPU core voltage will be generated. One is called the graphics core to the graphics section of the CPU, and the next is called the VCC core to the CPU. Step number 15. And once CPU received this power, he send out the serial signal that is called a SVID, voltage identification signal, saying the what level of power or what level of current is required from the VRM section. And he communicate with the VRM section. This is called the SVID signal to the VRM section. After step 15.1, the VRM section omit one signal that is called a IMVP power good or V-gate or the VRM power good. These are the different name could be found on the schematic diagram. It's called maybe IMVP power good, or sometimes called a VRM power good, or sometimes called the V-gate. All three names are the same things. Once the VRM section stabilize and this section omit one signal that is called IMVP power good, saying that entire VRM sections working fine, is sent to the SIO. Once SIO received this signal, now your all powers are okay, all power systems are working fine. So SIO omit one signal, that next signal is called the EC power okay or system power okay to the PCH, because PCH asked SIO to turn on all the power, and now he given the confirmation to the PCH saying that I done my job, my all power streams are working fine. Previously it was here 0 volt, now it's become a 3 volt, and once this 3 volt, this signal is called the system power okay. Once the PCH received this signal, system power okay, then he turn on this three signal one by one. The first he omit one signal that is called the DRAM power good, that means the RAM power good. That's step number 18. Once PCH send out this signal, CPU send out another signal that is called the DRAM reset. This signal you can check on the DDR3 RAM pin number 30. Here you should get a 1 volt. If you find a 1 volt here at pin number 30, that means PCH send the DRAM power good signal to the CPU, and CPU omit this DRAM reset signal to the RAM. Now is ready to communicate with the RAM. The next signal PCH send, that is called a CPU power good, and PCH saying to the CPU whatever the power you got, all the 4 level of power, that is called VTT, VCCP, CPU core and graphics core, all the power levels are fine, so you ready to work, that is 1 volt. And finally PCH omit one signal that is called a PLT reset, that is called a platform reset. At this point he reset the entire motherboard. It's a 3 volt comes out, and this 3 volt you can check on the Wi-Fi card pin number 22, or you can check this PLT reset at SIO, mention over there as the PLT reset, and this voltage goes to the CPU, reducing the voltage, because the CPU require only 1 volt. So PLT reset send out the 3 volt, so there they put a resistor, a current voltage dropping resistor, and the CPU reset finally a CPU reset signal. And once CPU got the signal, CPU get resetted and ready to work, and after a next clock CPU access the DMI bus, access the PCH and access this BIOS. This BIOS is called the PCH BIOS, and you can check at the pin number 1. Pin number 1 is my chip select, pin number 2 is a read. If you connect the oscilloscope here at pin number 1 and turn on the laptop, you will find some pulses like this, you will find some oscillation, and if this oscillation coming on the pin number 1, that means the CPU is ready and CPU got the reset and is accessing the BIOS. And pin number 2, he read all the data and pass to the processor. In this way we can see how the Quanta motherboard power sequence work. Thank you very much.
Hi friends, today we are going to learn fourth generations and fifth generations laptop power sequence. We are learning on this Compel motherboard. Okay, so this is Haswell processor, fourth generations, and this is my SIO, and we'll see the signals how they are coordinating with each other. So first we'll see this is my voltage sections where my adapter inputs and battery inputs goes inside. My adapter may be something 18.5 volt and battery 10.8 volt goes inside. So this out voltage is called the V in voltage. If it is both are connected, adapter and battery, then I'll get a adapter voltage out, that is 18.5 volt, and then this volt goes to the different department, different sections. So these are the pulse width modulator. These are the pulse. These are, here's a 2 pulse width modulator, 3 and 5 volt. Here are 2, 1 volt and 1.8 volt. Here is a 1.35 volt. Here is a 1.05 volt. And the last, here are the 2 pulse width modulator for the CPU core and the graphics core. So these, the gray color are the pulse width modulator. The input is adapter voltage is the input, and these are SIO KB9012 coordinating between this all the sections, and here is a processor, and this one is a bias. So first this voltage goes inside, this 18.45 voltage goes inside, it goes to the different section, and this always volt send out the voltage, that is called the linear voltage, and this linear voltage goes to the SIO. This voltage is called 3 VLP. So this 3 VLP volt goes to the SIO, SIO get power on, and SIO send one signal, that is called the EC on. So here we made a step. So P1, 2, 3, 4 is like a step. So we had to go like different steps. So first the voltage goes inside, then 3 VLP volt comes out, SIO get the power 3 volt, then SIO omit one signal, that is called a EC on. In this red color, the red color, that is a voltage, and this blue color, it's a signal. Okay, so this EC on signal comes out from the SIO if the SIO is okay, and it goes to this always voltage. In this section we'll see later on the schematic diagram how this signal goes. What we'll do, we'll see now only. We'll go to the schematic diagram. So now we'll see on the schematic diagram. So this is a Compel motherboard, and the motherboard number is LA-A621. This is a 38-page diagram. So first of all we'll go to the voltage sections, that is on the page number 30. This is my voltage sections. Okay, so we'll see how the voltages flow in this circuit. So here is my adapter input, 18 volt goes inside, and these are the MOSFET, and this is a controller chip. V in this number is BQ2472. These are the MOSFET. So my 18 volt goes from cross this MOSFET, then cross this second MOSFET, and comes here this current sensing resistor. This is a 0.2 ohms resistor, and you will see my adapter voltage will be here. You should check, you can check 18.5 volt here. If the 18.5 volt is not coming here, then the possible fault could be this 2 MOSFET, or this chip is not driving to this MOSFET. Okay, so this is my first section. So voltage should come here, and this voltage 18 volt goes to the different departments. So we'll see second, that is my always voltage, that is on page number 31. So this is my always voltage section. So you can see here, so there are two sections, section this and this is another sections. Okay, so in this first sections, this chip number is this chip number is location is PU401, the chip number is SY82088BQ and C. This is my 3 volt pulse width modulator. My 18 volt goes to pin number 8. Okay, and my 18 volt goes to pin number 8, and this pin number 5 is a LDO. This is a linear output. My 3 volt comes out from this pin, and this voltage goes to SIO. Okay, this 3 volt goes to the SIO power on. Now in these chips there are two sections, one is a linear voltage and another is a pulse width modulator. So the linear voltage, as soon as I give the input voltage, the linear voltage immediately comes out on the pin number 5. But for this pulse width modulator, these chips require an enable signal. Without enable signal, this section can't work. So in this section there are pulse width modulator and two MOSFETs also inside. So once this chips get the enable from this pin number 1, started triggering, and this pin number 10, the pulsating AC voltage comes out, goes to this coil and this 3 linear voltage, 3 pulse width modulator voltage out to here. Okay, so same way here also you can see, here is my 5 volt, same. In here goes the 18 voltage inside, pin number 7 linear voltage out. When you get the enable signal, this 5 volt comes out. So we can see in this schematic diagram how it's work. Now we'll go again back to our concept. So we see how this 3 volt and 5 volt comes out. When the sections is working fine, he send one omit one signal, that is called the SPOK. He send one signal that is called the SPOK, and this goes to the SIO. As well as this SPOK signal goes to this pulse width modulator also, this 1 volt and 1.8 volt pulse width modulator also. So once this SPOK signal comes out, he get enable signal to this 1 volt and 1.8 volt, and 1 volt comes out, this pulse width modulator 1 volt and 1.8 comes out, and this 1 volt and 1.8 goes to processor. So this is step number 6. So this is before powering on. Now we'll turn on the power button. So this is my power button, step number 7. So here is a 3 volt. As soon as I press a power button, it goes to 0. When I release button, again it goes back to 3 volt. So step number 7. So as soon as I press a power button, SIO emit one signal that is called the RSM RST. It's sent to the processor, because the PCH and processor is in single chips. So it send one RSM RST, the resume and reset, 3 volt comes out. Then within a 10 milliseconds of durations, he send another signal that is called a PM power button at step number 9. So if my processor is okay and if everything is fine, the processor send reply him a 2 signal. So now the entire power supply is turned on. He want to turn on, power supply is turned off, but he now want to turn on. So SIO send 2 signal that is called a SLP S3 and SLP S4. That is called a slip mode 3 and slip mode 4. So he omit the 2 signal, that is a step number 10 to the SIO. Once SIO received this 2 signal, that means previously it was a 0 volt. As soon as he send this signal, so here will be 3 volt. So as soon as SIO received this SLP3 and SLP S4 signal, SIO omit one signal that is called a system on to this pulse width modulator. In this pulse width modulator, when this he received this system on signal, this enable signal to the 1.35, this 1.35 goes to my DDR3 LRAM. Okay, so this 1.35 voltage will be generated and goes to the RAM, and its power good goes to the CPU, that is called a DDR power okay. That means the RAM got the power. This signal means that he is saying to the CPU that RAM got the power. That is step number 13. The next step is VR on signal, that is a step number 14. After system on, SI omit one signal, that is a VR on signal to this V core section, that is a VRM section. In this VRM section there are two sections, V core voltage and graphics core voltage. This is a step number 15 and 16. There are two voltage will be generated, and that voltage supposed to be 0.7 to 0.9, in between 0.7 volt to 0.9 voltage. So the two different voltage will be generated on the V core section, and that supply goes to the processor. That is step number 15 and 16. And then this sections, when it's okay, he send one signal that is called a V gate. The V gate signal means my entire CPU core section is working fine, and it goes to the SIO. After SIO got the signal, SIO send another signal, that is SUSP, that means suspend on. In this, see, you can see in this there are some circle we are made. So here are MOSFETs. So this signal name is called suspend. Suspend means the voltage will be generated already here at this point, but as soon as you trigger this MOSFET, that's step number 18, this voltage will be released to other side. Suppose here is a drain, and this one is a gate, and this one is a source. So as soon as the gate triggered to this MOSFET, the drain voltage pass to toward the source side. So same way here, this 3 volt always become the 3 volt suspend, 5 volt always become the 5 volt suspend, 1 volt always become the 1 volt suspend, and 1.8 and 1.35 like that. And finally he turn on this 1.05 voltage also, that is a system voltage 1.05, and this voltage goes to the processor. That is a step number 18. Okay, so in this way we can see how this entire sections works. Yeah, at the step number 19, the all voltage will be generated, and it goes to the different sections to the respective component. And this in step number 10, SIO omit one signal, that is called a KB reset. Step number 20, then at 21 he send one signal that is called a PMC core okay, power okay. That means the power okay signal. This signal means your entire power streams is okay. It's saying to the processor. If you check this signal, if it is here is 3 volts, that means my entire power stream is okay. So after 21 steps, then 22 steps, that is called the DDR power okay. And finally when CPU received this 20 power okay, finally CPU omit one signal, that is called a PLT reset, that is a platform reset. Is reset the entire motherboard including RAM and your network or audio or whatever it may be. You reset and this signal you can check on this SIO, or you can check on the Wi-Fi card port also. And finally at step number 24, SIO CPU start reading the BIOS. So in this way we can see how this sections work. Now we're going to see on the schematic diagram. Okay, so we'll go to the SIO page, that is on page number 23. Okay, so this one is SIO. And you can first you have to check pin number 9. here should be a 3 volt. This SIO is a U28 location and this SIO number is KB9012. Okay, we'll see the pins of the SIO. This pin number 9 is a VCC pin. You have to check a 3 volt here. That is my first steps. Then the next signal you have to check, that is called a EC on, that is on 112 pin. This is a EC on. When SIO received the signal, if it is SIO is okay, he send one signal that is called a EC on, that is pin number 112. Then SIO turn on both the 3.3 and 5 volt, and finally SIO received a SPOK signal. You can see on this side on pin number 25 SPOK signal. When the SIO received this SPOK signal, that means my always voltage is turned on. SIO, my always voltage, that means my 3.3 and 5 volt is working fine if you received this signal at pin number 25. Then the next is my 1 volt and 1.8 volt turn on, and then I have to press the power button. The power button is my 114, this pin 114. This is my power button. This is my power button. As soon as you press this to ground and release, one pulse is generated, 303 pulse to the 111 pin, and then SIO omit one signal, that is called a RSMRST pin number 100. If it is my SIO and the EC bias is okay, then here after power button press, here you should get a 3 volt. If you are not get a 3 volt at this pin after pressing a power button, that means my possible fault could be SIO or my EC bias. Pin number 100. The next is PM power button, that is the post power button or digital power button. On a pin number 106, it goes to the CPU saying this power button is press. Then SIO processor send two signal, that is called slip mode 3 and slip mode 4, SLPS3, SLPS4. From the processor you can see the arrow, it goes to pin number 6 at the SIO and pin number 14. It comes from the processor. Then if after receiving this pulse, SIO started turning on the different powers from different power streams. So he first turn on the system on signal, that is pin number 95. You can see pin number 95. This is called a system on signal. Here it was 0. Now after receiving this SLPS3, SLPS4 signal, this pin goes to 3 volt. That is system on signal is turned on. Is turn on the all the 1.35 voltage and all. Then 121, this is a core voltage VR on signal. Sorry, is turn on this VR on signal, and here my CPU core voltage will be generated, that is CPU core and graphics core voltage will be turned on. Then the next is V gate signal. V gate signal means pin number 97, that is a V gate. You can see V gate. One sec. Yeah, this one, pin number 97, V gate. Here it was a 0 volt, but when my core voltage turn on, that's VRM section is working fine. If my VRM section is working fine, then here I'll get a 3 volt. If I'll get a 3 volt here at pin number 97, that pin is called the V gate. That means my VRM section is working fine. Okay. The next is SUSP signal, that means suspend on, pin number 116. Pin number 116, suspend on. At this pin, the all power streams mode transfer always to suspend. And then KB reset, pin number 2, SIO send a KB reset signal to the processor, that is the interrupt. And then pin number 21, 32, pin number 32 is my PMC power okay. That means the all powers are okay. Pin number 32. We'll see where it is 32. Wait. Yeah, this one. This is my pin number 32, that is called a PCH power okay. And SIO sent to the PCH, or it's called a CPU, that is called a PCH power okay, or you can say the another name is a PMC core power okay. The PMC core power okay or the PCH power okay, that means my entire power stream is okay, and now proceed for the reset signal, that is a PMC reset. And finally CPU generate a reset signal that you can check on the SIO also. This one is my PLD reset. Here you will get a 3 volt. If my processor is working and he omit one reset signal, here you will get a 3 volt. So in this way we've seen how this 4th generation and 5th generation power stream work for the Compal laptop motherboard. Thank you very much. Hi friends, today we are going to learn Apple laptops adapter in and battery charging sections. So in the screen you can see there are some components. I'll introduce you first the component. So this is my adapter input, this is my battery input, these two supplies are input, and this section is the output. So within this section, these are the controller. This entire is a controller who take the voltage in from either from adapter or from battery. And on the right hand side corner there is one chip. This is called the SMC chips, system management controller chips. The system management controller chips work is to manage the power, manage the temperatures, manage the fans, etc. Now when we connect the adapter, the power goes in two directions, from this direction and from this direction. There are two directions, okay. So either if we can connect from the adapter, my power is go from here or and here. If I connect from battery, my power is go from here or from here. That means there are two directions of the power. So if I connect the adapter, my power goes to like this. You can see in this animation, it goes to this diode's anode, from diode cathode, and then it goes to this pulse width modulator. This pulse width modulator receives the 16.5 volt from the adapter and convert this 16.5 to 3.42 volt. Okay, it received 16.5 volt from this side, from the adapter, and convert into 3.4 volt, 42 volt DC. And this DC voltage, 3.42 voltage DC volt, goes to the SMC chips. So this SMC need a 3.4 voltage that goes to the SMC. Now SMC got the power on. The next is and the second thing here we are mentioned 1 2 3 4, like 1 2 3, then 4 5. These are the sequence, and that sequence the power goes. That is a rhythm of the power. Okay, so now the SMC got the power 3.42 volt. Next SMC need a reset signal. This small 6-pin chips generate a reset signal to the SMC. Now it is a 0 volt. Now it's become a 3 volt. It's become a 3 volt. So SMC got a reset signal, and now SMC ready to work. Okay, so the next is now we see how the power goes from this direction. In another way, the power goes in here also, on both the side, here and here. Now the power goes in this direction. You can see in this animation, power goes here. It stopped at that MOSFET. This is 8-leg MOSFET. These are the 5 MOSFET. This is controlled by this battery charging chips. The chips number is 6259, ISL 6259 chips. So now this ISL 6259 chips need a power to work. he get the power from this adapter. That pin name is DC in. DC in. That is step number 4. So now the battery charging get the power from this adapter, DC in 16.5. The next is AC in signal, adapter current in signal. This is a signal. It's supposed to come 3.4 volt at this pin. If 3.4 volt, 42 volt come here, that means this chip will come to know that is getting the power from the adapter. So here are two resistor, R1 and R2, which is current dropping resistor. We reduce the voltage and 3.42 voltage generated and sent to the AC in pin of this chips. So now this ISL 6259 chips, battery charging chips, got the power, got the signal. That signal known as AC in chip. AC in, that means adapter current in 3.4 to 42 volt. After receiving this signal, this chip omit one signal that is called AC OK. That means he received AC in, adapter current in is there, and he sent one signal out, that is AC OK, adapter current OK, and he sent to the SMC. Now the SMC come to know that he is getting the power from adapter. Here you can see everything is work on a logical basis. Okay, so SMC got the power from here, he's got the reset, then he's got the AC OK signal, that means adapter current OK signal. Now SMC will communicate with this battery charging chips with this SM bus. This bus is called system management bus. This is a two-wire communication protocol. SM data and SM bus is a two-wire communication. It's a bidirectional data bus. Like in the chips, they are communicate with each other. So at step number 7, here this ISL 6259 chips communicate with the SMC, and they communicate, and now this SMC will tell this chips you trigger this 2 MOSFET because the power comes in. Now it's to take it in. So this chip trigger this 2 MOSFET, trigger this gate. First he communicate with this chips, and after that he trigger this 2 MOSFET. You can see in this animation. Okay, so at step number 8 he triggered 2 MOSFET. After triggering this 2 MOSFET, the voltage which is halt here, which is stop here, now pass to the MOSFET, both the MOSFET, and pass to the next sections. So you can check the 16.5 volt at this current sensing resistor, the green color resistor, small resistor, which value is 0.02 ohm 1 watts. You can check this voltage at this resistor 16.5 volt, and if the voltage is not coming at this particular point, that means possible problem could be this 2 MOSFETs are not okay, or they may be open, or they are not getting trigger from this chips, or this chip is not getting AC in signal. Either any of this, you have to check previous sequence for that if the voltage is not coming here at this point. Okay, the next is the voltage goes to this MOSFET, MOSFET number 3. Here are 2 MOSFET, MOSFET number 3 and MOSFET number 4, and one coil is connected here, one capacitor is connected here, and this 2 MOSFET triggering by this chips, battery charging chips. Now my output sections require as 12.6 volt. Okay, my system need is 12.6 volt to work, but my adapter is giving a 16.5 volt. So here, and my battery is also 12.6 volt. So here I have to reduce the voltage to 12.6 volt. In this, with the circuit we are talking about Apple MacBook Pro models. Okay, so in Air this voltage could be the 8.6 volt. In Pro it is 12.6 volt. Okay, so in this we have to reduce the voltage, so that's why they use this circuitry is called the pulse width modulator. 2 MOSFET, upper MOSFET, lower MOSFET, coil and capacitor. Now once he received the signal from the SMC, the ISL 6259 chips started triggering this 2 MOSFET, upper gate and lower gate started triggering this 2 MOSFET. So here the plain DC voltage started chopping at this point, and pulsating AC voltage will be generated at across this coil. This coil will generate a back EMF past the DC voltage which is gathered across this capacitor, filtered it is, and sent to the output section, sent to the fuse, and output will receive a 12.6 volt pure DC output. So in this way we can see how the output voltage is coming out. If it is voltage is 12.6 is not coming across this fuse, then you have to check the back section which we explained just now. The next is, if now the battery need a charge, here is a battery, if this battery need a charge, so now SMC this communicate with this battery through the SM bus. Here also two SM bus is here. In this section we can find the two SM bus. One is here from SMC to this chip, and another is from SMC to this battery. So in next sections this battery communicate with this SMC chips, and he asks, I need a charge, you please send me a charge current. So after that SMC will give command to this battery charging chips, and battery charging chips will trigger this. He generate this signal charge B gate. He send one signal like this, trigger at this step number 12. Once he trigger this MOSFET, this voltage which is 12.6 coming here, it will flow like this. You can see in this animation it goes to this battery, and battery started charging. So that is step number 13. So in this way we just now see how this sections work in this Apple MacBook Pro laptop. Now we are going to see how the laptop work on battery. Now we have just seen how the laptop work on adapter. Now we are going to see how the laptop work on the battery in this next slides. In this slides, adapter is not connected, so the output voltage, the AC in is 0, DC in is 0, this is no power. So but the SMC need a power. So what SMC will do, he take the power from battery like this, and my 12.6 volt goes to this pulse width modulator, and this pulse width modulator will generate a 3.42 voltage, and this 3.42 voltage goes to SMC like this. Now the SMC got the power from the battery. Because of this voltage is absent, here the voltage is 0. So now this SMC will come to know that he is getting the power from the battery, and he started communicate with the battery like this through the SM bus. You can see this animation how they are communicating, and once they started communicating, the battery is sending a charge like this to this MOSFET number 5. He crossed the MOSFET number 5 because the gate voltage is absent. He crossed this MOSFET, goes to this current sensing resistor, and cross to this section and goes to this fuse. And in this way we can saw how the Apple MacBook Pro adapter current and battery section work. So thank you very much.
Hi friends, today we are going to learn Apple laptop power sequence. Here is some concept diagram in the screen. You can see I'll introduce some component first. This one is a processor, then this chip is called the SMC, then this chip is called the PCH, then the RAM. Okay, so these are the 4 major components in the laptop, and rest of the all power sequence. Now in this laptop there are 2 power input. One is called the adapter power input here, and another is called a battery input here. So these are my 2 power input. Now when I connect either battery or the adapter, first this voltage goes to this section. Now this section is called a 3.42 voltage generator. It's a small pulse width modulator who generate a 3.42 voltage. There is one chip, coil and capacitor. He receive this voltage from the adapter or from the battery and generate a 3.42 voltage. Now this 3.42 voltage is called a PP3042. This voltage goes to the SMC. Now SMC got the power. Now SMC is ready to work, but before that you need another signal. It's called a reset. SMC need a reset signal. So here is a small delay circuit who generate the delay for 10 millisecond, and he generate the SMC reset to the SMC. Now my laptop is ready to work. The next signal is called the SMC on off, or the power button, the power switch. Now here is the voltage is the 3 volt, and the switch next terminal is connected to the ground. Now if I press the power button and release the power button, it generates the 303 pulse at here. Now when a 303 pulse is generated at this terminal, SMC come to know that the power button is pressed, and he send out this signal. It's called SMC underscore PM underscore G2 enable. Now he send out this signal, and here is a pulse width modulator, or different pulse width modulator who generate a 3.3 and 5 volt. Basically here is a use a TPS 51125 chips. So when he receive this enable signal from SMC, he generate a 3 volt, 3.3 volt. Okay. Now if this signal is not come out from this SMC, that means the possible fault could be SMC. My SMC is faulty. And if SMC is not receive this 3.42 voltage, that means this 3.42 volt generator circuit is faulty. So if the SMC chip is okay, he send out this signal. Then there is a 2 enable input on this section. One is for a 3.3 volt enable, and another is 5 volt enable. But before that, here is one more section. It's called the battery in charging section. When he received the 16.5 volt, he convert into 12.6 volt. That we seen in our last video. In this section, he received this 16.5 volt and convert them into the 12.6 volt, and this 12.6 volt comes here, and this voltage is spread entire the motherboard, is sent to the for the battery charging also. If the battery discharge, this voltage pass to the battery charger also, to the battery also, and this voltage is called the volt-in voltage. It spread the entire vein section to the input to the all pulse width modulator. Here are the different pulse width modulator. This for the 0.75 1.5 volt pulse width modulator. Here is a 1.05 volt pulse width modulator. Here is a 0.85 VCCPA pulse width modulator. Then the VRM section. Then this 3.5 volt pulse width modulator, and of course last the LED backlight. Now this 12.6 volt is already generated, and I already pressed the power button. So SMC send out this signal, SMC PM G2 enable signal to this pulse width modulator. Now 3.3 volt is generated at step number 7, and this section send out a power good signal to the SMC, confirming that this 3.3 volt is generated. Okay, so the 3.3 volt is generated. Now this goes to the SMC, and this volt goes to the PCH also. Now PCH got the power, PCH ready to work. After that, SMC send out next signal. It's called a PM power button to the PCH. The PM power button signal, the pulse is generated here. A 303 pulse is generated here. Once the PCH received this pulse, then he is ready to work, and he send out the next signal. It's called PMSLP underscore SUS signal, and this signal enable 5 volt. This signal enable 5 volt, and now my 5 volt will be generated. In this section there are two enable, one for the 3.3, another is for 5 volt. One coming from the PCH, another coming from one coming from the SMC and another coming from the PCH. Now my 5 volt is also generated. If the 5 volt is not there or not coming, that means maybe this pulse width modulator faulty. So the next is step number 11. When he received this voltage, when this voltage is turned on, this PCH send out one signal that is called SLP-S5, a slip mode 5. That means a 3.35 volt is ready to work. He send out this signal, and then SMC send out the next signal is called the PM RSM RST, resume and reset. He send out a resume and reset. So if you have a laptop and which is not powering on, if it is dead, then what you have to check is, first you have to check this 3 volt, then 303 pulse. If the 303 pulse is coming, then you have to check this pulse. If SMC just G2 enable signal, if it's not coming, then SMC faulty. Then you have to check this PM power button. After that PM power button, you have to check PM SLPS3, and if this signal is not coming, then possible fault could be the PCH. Then the next signal you have to check this two signal, that is called SLPS3 and SLPS4 to the SMC. And if this signal is not coming, then of course again then power won't turn on. So if this signal is not coming, then possible fault could be the PCH. Okay, then now the next is PCH send out this two signal, SLPS3, SLPS4, and PCH also start sending this sys clock. The sys clock, the SMC need a 32.7 kilohertz clock. Now you can check this clock also with the help of oscilloscope. If this signal's sys clock is coming, that means SMC got the power and he is sending this clock to the SMC. PCH sending this clock to the SMC. Okay, so next is, if all these three signals are coming, that means the PCH is okay, PCH is working fine. Then he is going to turn on this pulse width modulator one by one. So this SLP3 and SLP4, first this SLP4 signal goes this section also, here SLP4 is coming here also, and then he turn on this 0.75 and 1.5 voltage. This 1.5 voltage basically goes to the RAM and the PCH. If it is a RAM is a DDR3, then the voltage will be 1.5, and if it is a RAM it's DDR3L, then the voltage will be 1.35. Then you can check this both the voltages at the coil, RAM voltages. Okay, the next is when PCS send out this SLP3 signal, it goes SMC as well as it goes to this two pulse width modulator. One is generate a system voltage, that is 1.05 volt. The 1.05 volt comes out, and this 1.05 volt goes to PCH as well as to the CPU. Then he turn on the next voltage is called the VCCA voltage, PVCCA voltage, that is supposed to be 0.85 voltage. and this voltage goes to the CPU. Now this all pulse width modulator have their own power good signal. When this 3.35 volt is ready, this 5 volt is ready, he send out one power good. When this 1.5 volt is ready, he send out one power good. When 1.05 volt is ready, he send out one power good. When this VCCA voltage is ready, he send out one power good. Then all power good join together and they generate the next signal is called all system power good. The all system power good means the all powers are ready except the CPU core voltage. If one of the voltage is not ready, if one of the voltage is absent here my voltage will be 0. And if the all voltages are ready, if all voltages are working fine, then here 3 volt will be generated. If this all system power good is ready, here is my 3 volt and this 3 volt goes to the SMC. Now the SMC will understood all system voltages are ready and he send out the next signal is called the VR on signal. Here is a VR on signal. The VR on signal he send here the VR on signal means he asks the CPU core section to turn on, and then when the VR on section is ready, he turn on 2 core voltages. One is called the CPU core and another is called the graphics core. It's called the PPVC core, and the GFX is called a PPV core AGX, and this both the voltage given to the processor, this both the voltage going toward the processor. Now when both the voltages are ready to work, then VRM section generate the next signal is called the CPU IMVP power good to the PCH. This CPU IMVP power good signal comes out from the VRM section. That means my core section is ready, and once the PCH received this signal, he started sending these 3 signal to the CPU. One, he sent the PLT reset, send the CPU PLT reset. At this point PCH sent this PLT reset and reset the entire motherboard. He sent out the 3 volt, and here they kept one resistor to drop the voltage, and 1.05 voltage will be generated, and this voltage is called a CPU reset. Then the PCH send the next signal is called the CPU power good, saying the CPU power is okay, now ready to work. And finally he send on step number 21, he send out a DRAM power good signal. The DRAM power good signal means the RAM supplies is okay. When the CPU got all this 3 signal, he got all the power, he's ready to work. And at step number 22, he send out at RAM pin number 30 a DRAM reset signal. A DRAM reset signal means reset the RAM and start communicating with the RAM, and in this way my entire motherboard is ready to work. In this way we learn the power sequence of Apple laptop. If you're having a problem in laptop which is hi, today we are going to check Apple MacBook Pro. This model number is A1278 and motherboard model number is 8202936. In this video we'll see to read the schematic diagram, then we'll see board viewer, and we'll see the concept diagram and the actual diagram. So this one is my concept. Okay, so this one is my concept. In this concept this is SMC, then CPU, then PCH, and When I connect the adapter, at that time 16.5 volt goes to two direction. One is here, another is here, and this section generate a 3.42 voltage, and this 3.42 voltage given to the SMC. So SMC get power on here, and next signal is SMC get a reset signal. Plus in this side, when the 16.5 volt given to this section is called adapter in battery charging section. Adapter in and battery charging section generate a 12.6 volt output. Is take 16.5 and generate a 12.6 volt out, and this 12.6 volt is given to the different pulse width modulator like this. This 12.6 given to this 3.3 and 5 volt generator, then 0.7 and 1.5 volt generator, then 1.05 volt, then VCCA voltage, then VRM voltage, and of course LCD backlight or LED backlight. So this is my V in voltage given to the different section, plus this voltage given to the battery also for charging purpose. But when the adapter is absent, at that time the battery voltage pass from this MOSFET, and this voltage again given to the different MOSFET, plus different pulse width modulator, plus this 12.6 voltage given to this 3.4 to this thing also, 3.4 volt to pulse width modulator also, and this is given to the SMC. So SMC get a power from the both the side, either from the adapter or from the battery. So now we'll go to the diagram. First we'll see the boards. This one is my board. The number is here. This one is the number 820-2936-B. So we'll open a diagram for this. This one is diagram. It's a 86 page diagram, and now in this motherboard there is a there is not a location number. There is no location in this motherboard. So for that reason they given a board viewer. So we had to use a TP-Link software, a program, and we had to download the board viewer. So see, this is a TP-Link. This is a software. I had to run this TP-Link, and then I had to open a program for this. Yes, BRD file, BRD extension for the board viewer. So Apple 1278-820-2936, the same as schematic. So I have to open this. So this is my board viewer. Now the first thing in the schematic, I have to find 3.42 voltage in this. This one is a block diagram, and this next page number 3 is a power sequence. And in power sequence you can see there are two inputs. One is this adapter inputs, and another is this one is a battery inputs, and this section is called the 3.42 voltage generator. So now any laptop, first of all, this volt should be generated. This 3.42 voltage should be generated. So when when my adapter connect, then this 16.6 volt travel from here to here and here, and this department generate here a 3.42 voltage at here at this junction. So this section is on page number 63, and I'll go to page number 63. This one is my page number 63. Here is my input, and this adapter and battery voltage come together, and this chip, location of this chip is U6990. This one is called the location number, and the chip number is PM6640. PM6640 is the chip number, and U6990 is a location number. So in pin number 7, this one is a pin number 7 is a V-in pin. There is a input pin, there is a supply pin. It's come from the adapter or from the battery, and this pin number 6 is given to this coil. Location is L6995, and this one is a capacitor. And here you send out a 3.42 voltage out to the SMC. Now I have to check here at this coil, or I can check at this capacitor. So I have to locate first of all this coil where it is. So I should get a 3.42 volt here. Now if the voltage is not coming here at this point, that means there are one or two possibilities. One possibility is that either supply is not coming at this pin number 7, or this chip itself may be faulty. So I have to check 3.42 voltage at this coil. This coil location is L6995. So what I'll do, I'll select this L6995. I'll make a copy, and I'll go to the board viewer. I'll go to this component. I'll paste here, and then search. Now see. Just make it enlarge. So see, this L6995 coil. So here I should get a 3.42 voltage. That means on the pictures, you can see the pictures. This one is this coil. I should get here a 3.42 voltage at this terminal. If voltage is not comes out here, then the possible fault could be my chip. That chip number is, I have to put back again, same thing. Oh, 6990. See, this one is the chip. So U6990. So U6990 is here, and in board this U6990 is here. So here I have to check the inputs and output. In 6990 I have to check at pin number 7 16.5 voltage, and VCC voltage here, and if the voltage enable also here, and this voltage is coming, then still voltage, if the still voltage is output voltage is not coming, then the problem in the chips. So this is the first step we have to check. The next thing we have to check is a reset signal. We'll come back to page number 3 again. So we got the 3.42 voltage at SIO, sorry, in SMC. The second we have to check SMC reset. SMC reset is a delay signal. Here also we should get a 3 volt. So same thing. We have to go on page number 44. We'll straight away find out from here. The signal is called SMC reset L. We'll copy it, go to the board viewer. Now we'll select the net. Net means the component. We'll paste here to next. So this one is my location. So this one is my location, this white dot. So here I should get a 3 volt. Okay, so on the board we can see opposite side, this opposite side, at this here, that means at here, here somewhere. So you have to find out. So this one is my SMC. The next component, next signal we have to check, that is a power button. So this one is my SMC, and next this signal is called SMC on off L. This signal SMC on off L. The SMC on off L is a power button signal. It goes to the keyboard and the on off switch on the keyboard. So suppose if I remove the keyboard and now I have to turn on and off, so that time I have to short this pin. So how I locate? So first select this signal name. One sec, just wait. Oh no, I'm not coming. Just copy, go to the board viewer, go to the net, put paste. Okay, then signal is here somewhere. That means here at this one is a keyboard connector, this side, and the signal is here somewhere. You can see here this one. Here. So this one is that pin. We have to check 3 volt here. You can check 3 volt here also. If 3 volt coming here, that means obviously SMC got a 3 volt. Now you can short this pin to the ground. The laptop should turn on. If it's not turning on when you are shorting this pin, that means at here, this terminal, here, this white dot, that means there is something problem. So the next thing you have to check, that is SMC P2 G2 enable signal. SMC P2 G2 enable signal, it's coming out from the SMC, and if this signal not come out from the SMC, then the problem in the SMC. So select this signal, net SMC G2. Wait, we'll try from here. Yeah, this signal. Okay, we'll go to the next signal. It's not coming here, so go to page number 3. Go to this SMC, and now we have pressed the power button, and now the supply should come out. If not coming, then the next signal we have to check, that is PM power button. You can straight away check this signal, PM power button coming out from the SMC. So we'll go to here, PM. You can check this signal, then straightway we'll copy and paste this signal. Make a copy, we'll come to the board viewer, we'll go to the net, we'll go here, paste, yeah, here at this terminal, or you can check here also. You can check at this point PM, that means on the board side. You can check on the top of this portion, that means somewhere around here, or somewhere around here, this dot PMG2 enable. Here you will get a 303 pulse. Here you will get a 303 pulse. If 303 pulse come out from this one is my SMC. So here this one is my SMC, and now this PM power button L coming out from the SMC, and if this signal is not come out from the SMC, that means probably SMC is bad. So we have to replace this chip. So here I should get a 303 pulse. The next is, if PM power button L its signal is okay, then the next signal we have to check, that we can check the RSM RST also from SMC to PCH, and we can check SLP3 and SLP4 also. SLP3 PM power button, this RSM RST signal coming out from the SMC to the PCH, and PCH send out these two signals called slip mode 3 and slip mode 4, that is SLPS3 and SLPS4 signal to the SMC. So we can check this two signal. We'll go here, we'll check straight away SLPS4, copy. This signal comes out from the PCH. After power button press, this signal should be a 3 volt. So we'll come back to the board viewer, we'll connect here, paste, next. This test point is this side. That means this side, this corner. That means this corner. That means this corner. Okay, so we enlarge it. Here, so here, 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 this point, this white dot, here we should get a 3 volt after power button press. And if this RSMRST and PM power button signals are proper, they are coming, but SLP S4 and SLP S3 signal is not coming out from the PCH, then probably problem in the PCH. But before that we have to check the PCH RTC reset also, and 32.7 kilowatt crystals also RTC clock. And if the RTC is okay and the crystal is okay, power is okay to the PCH, but still SLP4 signal is not coming out, then the problem in the this one, the PCH, this we have to replace this chip PCH. Okay, so we see how this circuit work. So what we did now, we check supply, then we check reset, we check this power button, then we already check power button out, RSMRST, then straight away we check SLP3, SLP4, we check SLP4, and if this is not coming, then this is a faulty. If this both signals are not coming, then the SMC faulty. If the voltage is not coming, then this section is a faulty, and here is a 12.6 volt not comes out, that means this section is a faulty. So these are the compulsory signals. So suppose all this voltage is now the SLP3 and SLP4 signals also come out from the PCH, that means the PCH already given confirmation to the SMC to turn on. Now what is happen is this SLP4 and SLP3 signal straight away pass to this section like this. So SLP4 straight away pass to here to turn on this, and SLP signal straight away pass to here and here. So straight away is given enabled signal to 1.5 and 1.05 voltage plus VCCA voltage. So this signal, so you can check all this coil in this motherboard. You can see here these are the different coil, this motherboard. This one is for the CPU core, graphics core. You can check voltage on the rest of this coil. Here you can check 1.5 then here you can check 1.05 like that. You can check here 0.75 voltage like that. So all this voltage supposed to comes out, and finally this is the CPU core voltage, 2 coil, and this 3 coil, 2 coil for the CPU core, 1 coil for the graphics core. When this all voltages are okay, at that time when the all voltages power goods signal join together each other, you can see here all power goods are comes out and they join together and they generate a signal that is called all system power good signal. The all system power good signal, we can check this signal. See this one, all system power good signal. So we can copy this signal. We'll go to the board viewer, we'll go to the net, paste here, select this one. That means here below this coil, that means here this point, here this point. You can enlarge. Okay, so this 820 point, this all system power good signal, all 5 power good voltages, all this 1 2 3 4, all this 5 voltages are generate and they send out a signal, power good signal. All power good signal join together and a new signal will be generated, that is called as all system power good. That means all powers are okay, and this signal given to the, you can see this signal given to the SMC. And now when SMC received this signal, all system power good, then he send out the next signal, that is called CPU IMVP VR on signal. He send out the next signal, that is CPU IMVP. Now if the SMC received this signal, he received the 3 volt here but is not sending out this VR on signal, then SMC is faulty. But SMC is not receiving this signal, here it voltage 0 only, that means at this terminal voltage is 0 only, then one of the voltage is missing. Okay, so 3 5, then 1.5 1.05, and then VCCA, these are the 4 and 5 supply. One of the voltage is missing, then we can check individually each supply, which supply is missing, and we can focus on that particular supply and rectify the problem. Okay, so now we'll assume that this all system power good signal is okay. Then we can check next signal is that is VR on signal, and finally this voltages CPU core and graphics core. The signal name is see, this is a PPV core. These are 2 signal. These are the 2 signal. So we can check this signal. Sorry, not signal. These are voltages. This one is a CPU core. This voltage approximately 0.9. Approximately. We'll go to the net. Select here. Okay, so here we get a CPU core voltage. You can check the CPU core voltage at this. Where is the mention 932? You can check here. That means above the processor. That means on here you can check CPU core voltage, and of course the graphics core voltage you can check. And if these voltages are okay, then the motherboard is ready to work. Then you send out one by one signal. So in this way the motherboard turn on. After that the PCH will receive this IMVP power good signal. Then you can check this IMVP power good signal, and in this way the motherboards turn on. So thank you very much. Hi friends, today we learn CPU functions, CPU test points, and how to identify the processor, different types of processor, because there are varieties of processor in the market. Intel itself, there are so many processor, their generation, then i3, i5, i7. So we'll try to understand the different types of processor and their powers. So first of all, we'll see CPU sockets. You can identify the processor by seeing the sockets. There are, if you open a laptop motherboard, you will find different types of sockets. Like if you see only the Intels, there are varieties of socket like this. If it is in older days, the socket like this, it's called the 478 MB. In this socket, the processor used in this socket is, it's called the Pentium M or Celeron processor. Now there is a 2-pin missing in this 2 corner. You can see in this 2 corners that the 2 pins are missing. So this socket is called the 478 MB. It's a use Celeron processor. Is the next generation is called socket. It's called the 479. The 479 socket, there is only 1 pin is missing in this corner. In 478 there are 2 pins are missing, and 479 there is only 1 pin is missing. The processor used by this socket is Pentium M or Celeron M, the next generation processor. And after that there is another socket, this called the socket P or socket 478 MN. In this socket there are 2 pin missing in this corner, like that. There are 2 pin missing. In this 479 there is only 1 pin is missing, but in 478 MN there is a 2 pins are missing in this corner. And the processor use this socket is called the Curso. And after that there is a 470 another generation, next generation processor is called the socket M, something yellowish color, and there is a 2 pin missing. Same thing, but there are 2 pin missing vertically. Here is a 2 pins are missing in horizontally. So this is a difference. So this processor won't fit in this, and this processor won't fit in this, like that. So everyone have their own sockets. And this processor, the Curso Xeon dual core processor used by this sockets. In 2010, Intel introduced Core i series processor. There is a different processor introduced, like a Core i3, i5 and i7, and there is a different generation from generation 1 to generation 7. But today we'll see only there are 3 generation 1, 2 and 3. So in Core i series, the socket, there are 3 basically socket used if it is processor used in a socket. First, this is a socket 879 socket. There is only 1 pin missing. In 989 socket. In 989 socket is called a universal socket, basically used for generation 1 or generation 2, or sometime it's used a Core i7 processor. The next socket is called for the generation 1 processor, that is a 4988E socket. It's basically used for the first generation processor, generation 1 i3, i5 or i7. And this next is 988B. This socket is used for generation 2 and generation 3 processor, Sandy Bridge and Ivy Bridge processor. Both processors are exchangeable from generation 2 to generation 3, like that. So these are the 3 main sockets used in a Core i series. After that there is no socket. All the processors are planted, are soldered in the motherboard. So the next slide will see what are the things required to processor work. What are the input signals or voltages is required to processor run. First of all, the processor need a power. Without the power, processor can't work. So processor need a power. So this Curso, this processor is a Curso. This number is mentioned here. This code number RH80636, and parameter is mentioned here is 1.73 gigahertz. 2 MB cache RAM, and 533 is FSB, front side bus. So this is a parameter for the processor, and the power is required. 3 level of voltages he require. The first is processor require 2 voltages. One is called the VCC, another is called the VTT. The VCCP is supposed to be a 1.05 volt, and VTT is somewhere from 1.05 to 1.2, but something around 1.1 volt. These are the 2 basic voltages is required to the processor. The next is processor required. This final voltage is called the CPU core voltage. This voltage actually considered in a current, not in the voltages. This 2 voltages is considered in the voltage, but this voltage power is considered as a current. So it's required more than 30 ampere current to processor work. And when this power, when this both voltage are stabilized, at that time this section is called the VRM section, VRM voltage regulator module. There are 2 pulse width modulator and they parallelly connected to each other, so they generate a more current. So once this 2 power got to the processor, after that this VRM section get this signal is called the VR on signal. The VR on signal is a signal, this 3 volt signal turning on the VRM sections. So once he got the signal, VRM section got this VR on signal, after that this VRM section generate a CPU core voltage and given to the processor, that is somewhere around 0.8 to 1 volt or 1.1, something here and there. This voltage is not fixed, but something 1 volt here and there, but this voltage is considered as a current. It's more than 30 ampere current. So once this processor got this voltages, he communicate with the processor asking his requirement, and this 2-wire communication from processor to VRM section, that VRM chip, it's called the SVID signal, serial voltage identification signal, communicating between the processor and the VRM. Once the processor got all this power, after that South bridge or the ICH generate one signal that is called the CPU power good signal. The CPU power good signal is a signal saying to processor that whatever the power you got, it's working, it's perfect, and you now ready to work. It's 1.05 voltage, and after that the MCH or the North bridge generate the reset signal. It's called the CPU reset signal, that is something 1 volt. And once the processor get reset, now the processor is ready to work, is ready to access the external devices. But before that he got the clock also from this clock department, and the clock started functioning. And now how will identify whether its processor is working or not? When he's receive all this, you can check all this signal by a multimeter. Either you can use a CPU socket tester also. There is a CPU socket tester is also available, and you can check this this signal by oscilloscope. You can check the signal on this front side bus FSB signal. It's called a B clock ITP, or somewhere on the debug port also. It's called the ITP XDP debug port. You can check the signal by oscilloscope at step number 9. And once this signal is coming, that means processor is function. So in this way we see how this core to Duo processor work. Now we'll go to the next slide. In next slide we'll see the different generations of the processor. There are number of generations from generation 1 to generation 7. There are lot of improvement in the processor, like previously there is a dual core or core to Duo processor. Then in 2010
Intel introduced Core i3 processor, i5 and i7. They introduced a 3 processor. The difference in 3 processor is like that the number of cores. First, the difference is. Number 2 difference is the cache RAM. In Core i3 there is a limited cache RAM, Core i5 there is a more cache RAM, and Core i7 there is a more cache RAM further. And then the turbo, like that. So these are